Alrighty, we're going to talk about the pH scale today. So it should be something that's familiar. I'm sure you've heard the pH scale since you were in elementary school. But now we're going to talk about what exactly it indicates and how we can calculate pH all by ourselves. Really, though, to understand pHs, though, we first have to understand the definition of an acid and a base. And for that, we're going to go to my man Arrhenius. So naming types of chemicals isn't like naming types of dogs. You can look at a dog and say, I think I'm going to call that one a Labrador. But with acids and bases, we can't really see them. They all look the same. If you look at hydrochloric acid or sulfuric acid or sodium hydroxide, a base, they all look alike. They look like clear liquids. So what is it that makes an acid and a base? And how is it that they first defined them? So for this, we're going to go to Arrhenius. So he was a chemist way back in the day, and he defined acids and bases according to these two definitions. So he said that an acid is something that produces H+ when dissolved in water. So he said an acid was something that produces H+, not just H's. Okay, it's something that ionizes in water, breaks apart, is aqueous. And when it is aqueous, when it ionizes, it makes H+ in the water. So an example of an acid then would be something like nitric acid, HNO3. So when we put HNO3 in water, it is aqueous, which means, we know this from the solutions unit, it does not stay as HNO3. Instead, it breaks apart into H+ and NO3-. And it is this guy right here, that H+, that it's producing in water, that makes it an acid. So Arrhenius said that nitric acid, HNO3, is an acid because when you dissolve it in water, it breaks apart and produces those H+, and that makes it acidic. That gives it all the properties that we define as acids. On the other hand, he said that bases produce hydroxides in water. So when you dissolve an acid in water, it makes H+. When you dissolve a base in water, though, it makes OH-. So an example would be sodium hydroxide. When you dissolve that in water, because it is aqueous, it doesn't stay sodium hydroxide. Instead, it breaks apart into sodium and hydroxide. And it's this guy right here, that OH-, that sodium hydroxide produces in water, that makes it basic. And the last thing that Arrhenius said was neutral. Move that up to the top so I have room. So something that is neutral has concentrations of OH- that is equal to the concentration of H+. So remember, those little brackets mean concentration and molarity. So a neutral compound, a neutral substance, is one that has equal numbers of hydroxides and H+. You have just as much base as you do acid, therefore it is neutral. If you throw off that imbalance and you wind up with more H+ than OH-, bam, you're an acid. If you throw it off and you wind up with more hydroxides and H+, wham, you're a base. That's how it works according to Arrhenius. This is the most basic definition, and it's probably the best one for a general chemistry class. Hey, before you think the wrong thing, acids, real quick, do have hydroxides in them. It's not that acids only have H+ and bases only have OH-. An acid is something that has more H+ than OH-. A base is something that has less H+ than OH-. And neutral is something that has an equal number of H+ and OH-. Water has H+ and OH-, but it has the same amount of both, and so it's neutral. Hydrochloric acid, it has hydroxides in it. Even though it's an acid, it produces H+, but it has more H+ than it does OH-. All acids have hydroxides, they just have more H+. All bases have H+, they just have more OH-. Okay, so keep that in mind. Acids have hydroxides, bases have protons. And just as a reminder, H+ is the same thing as H3O+. Alright, ladies and gentlemen, here it is, the unveiling of the pH scale. pH is molarity. It's just another way of writing molarity, and we write it on the log scale. Oh yeah, so if you remember logs from math, here we're going to use them in a practical application, and that practical application is definitions of acids and bases, the pH. So first off, the pH scale. If we have a concentration of hydrochloric acid, so if we have a jug of hydrochloric acid in our back room, that's 0.001, and another one, same substance, hydrochloric acid, but this one is 0.01. So the pH of this top one is going to be 3, and the pH of this one right here is going to be 2. So what I want you to get from this is the difference between pH of 3 and pH of 2. And remember, as they go down the pH scale, they become more acidic. So pH of 2 is more acidic than pH of 3. This is just 1 unit. So pH increased by 1 unit. But the concentration, so from here to here, that is 10 times more concentrated. So when we change the pH unit by 1 unit, that means the concentration is 10 times greater. So this seems like a small step to the eye, but really, on the chemical definition, it's increasing tenfold. That means if you go up by 2 pH units, so if we were to go down to pH of 1, the difference between pH of 3 and pH of 1 would be 100 times more concentrated. Let's take a look at 2 bases real quick. So we can recognize both these as bases because they have hydroxides in them. So the Arrhenius definition says they would be bases. This one has a concentration of 0.00001 molar, and this one 0.001 molar. So these two, the difference between those is the bottom one is 100 times greater concentration. So 100 times more concentrated. And then the pH of these two, keeping in mind that since they're bases, the pH will be above 7. So the pH of this top one would be 9, and the pH of this one would be 11. So it's just increasing by 2 units, but the concentration is 100 times greater. So what I want you to get from that is the pH scale is a very, very condensed range for the acids and bases. So it looks like small increments, small changes, but really they're great changes that happen over the different concentrations. With that, ladies and gentlemen, following along at home, how to calculate your very own pH. So the lowercase p in pH stands for something. It stands for negative log of fill in the blank. So negative log, literally a negative sign in front of the log on your calculator of whatever it is. So we actually use P a lot in AP chemistry. There's pKa, pKb, pH, pOH. So a lot of different things that use that little P in front. pH is the most commonly recognizable form, and we're going to use that one and one other one. So it literally means the negative log of whatever's next to the P. So P of H means the negative log of what? You got it, H. And more specifically, the concentration of H plus inside of the solution. So if you know the concentration of a particular acid, you can figure out what its pH is by taking the negative log of that concentration. Okay, here's 2 examples of acids that are in my back room. So nitric acid, let's say we have a bottle of it and the concentration reads on the side 1.5 times 10 to the negative 5th molar. We also have a bottle of hydrofluoric acid, 2.3 times 10 to the negative 3rd molar. Both very, very dilute concentrations, but we can figure out their pH by taking the negative log of the H plus concentration. So remember, HNO3, that's aqueous. That's an aqueous compound. It's soluble. All nitrates are, which means it's not really HNO3. It's H plus and NO3 minus broken apart. So that means the concentration of H plus in the solution is going to be 1.5 times 10 to the negative 5th. So if we take the negative log of this number right here, we can figure out the pH. And the pH of this particular one, negative log of 1.5 times 10 to the negative 5th, is 4.82. And the pH of this hydrofluoric acid, which has a concentration of 2.3 times 10 to the negative 3rd, the negative log of that would be 2.64. Type those into your calculator and make sure that you're getting the same numbers, that you know where your log button is, and that you have a log button on your calculator. If you don't, you're going to need to get a calculator that has one. You're going to be using logs a lot during this unit. Alright, now I'm going to show you how to go backwards from the pH instead. So let's say we look at a particular acid and we see that its pH is 3.25. How do we figure out then what the concentration of H plus is inside of that acid? Well, it's simple. So we just do the antilog, which is actually on your calculator. So this is algebra, just rearranging it. It winds up being 10 to the negative pH. So 10 raised to the power of the negative pH. So this example up here of our jug of acid, we're going to say the concentration of H plus is equal to 10 raised to the power of negative 3.25. Type that into your calculator, check to make sure you're getting it, and you should find that it is 5.6 times 10 to the negative fourth. And since we're dealing with concentration here, that would be molarity. Okay, so to go backwards from pH, it's just 10 to the negative pH. Do not forget this little negative right here. If you forget the negative on the negative log thing when you're calculating the pH, it winds up being okay. But if you forget this negative, you'll get a completely off number. Try it real quick. Do 10 to the 3.25 instead of 10 to the negative 3.25 and see how different your number is from this one. So do not forget that negative on the pH. Next, we're going to look at how you would calculate the pH of a base. So the trick with bases and finding their pH is that if we look at the concentration of sodium hydroxide, so NaOH, let's say we have a sodium hydroxide solution with a concentration of 6.32 times 10 to the negative fourth molar. Okay, so with a pH calculation, we would do the negative log of the H plus concentration, but sodium hydroxide has Na plus and OH minuses. So there is no H pluses in the formula. So then how do we get the pH of a base? Well, remember, so a base, it's not that it doesn't have H pluses, it's that it has less H pluses than OH minuses. So there is some H pluses inside of a base. They're just hidden. So instead, we need to start off by doing a pOH calculation. So remember, pH is the negative log of the H. So what would pOH be then? Yeah, you're right. It's the negative log of the OH concentration. So pOH, which we can use to get bases, is going to be the negative log of the concentration of OH minus. So that means for our example right here, when we're dealing with the pOH, we would do the pOH of the negative log of the OH minus concentration. So that would be this guy right here. And it tells us that the pOH is 3.20. Right. So from bases, we can't directly get the pH. We have to first get the pOH, and then actually it's pretty simple conversion from pH to pOH. And here is that conversion. So pH plus pOH always equals 14. So that means if pOH is 3.2, you're just going to subtract 14 minus 3.2, and you would find out that the pH of this particular solution is going to be 14 minus 3.2, that's just rearranging that, and it's going to be 10.8. So to find the pH of a base, we first get the pOH by doing the negative log of its concentration, and then we convert it to pH by subtracting the pOH from 14. Going backwards from the pOH, so let's say we wanted to find what the OH minus concentration is based upon the pOH. It's the same deal. It would be 10 to the negative pOH. So 10 to the negative pH will give us the H plus concentration, but 10 to the negative pOH will get us the OH minus concentration. So keep those two separate, and don't forget the negative on either one of them. Whoa, that's a lot of equations and a lot of information. Let's put it into a much simpler to follow explanation. So here we go. There is basically 4 different things we're going to have to calculate during this unit. And here is a little diagram that we can write down. Put this somewhere in your notebook, like the top of the page, and circle it. And go back to this whenever you're doing pH calculations until you kind of get the hang of it. So first and foremost, pH plus pOH always equals 14. Remember that, okay? You're going to make that conversion a lot. It's pretty simple, but you don't want to forget it. Here are the other 4 pieces of information you're going to have to calculate. The first one is the concentration of H+. And from the concentration of H+, we can go either direction and get the pH. From pH, we can go either direction and get the pOH. And from that, we can get the concentration of OH-. So the 4 things you're going to have to find during this unit are H+, pH, pOH, and OH-. And if you have either one of those or any of those 4, you can find the other 3 just by following kind of this pattern. So to get from H+ to pH, we use the negative log of the H+ concentration. So if you want to convert from H+ to pH, negative log of that concentration. If you want to go backwards, so this direction, that's 10 to the negative pH. So if you have the pH and you want to find the H+ concentration, you would just do 10 to the negative of that pH. If you have the H+ concentration and you want to find the pH, you just do the negative log of that concentration. If we want to go from pH to pOH, which we can also do, we're going to do 14 minus the pH, and that will give us the pOH. To get the pH from the pOH, 14 minus the pOH. So what hopefully you can see right now, if we have the H+ concentration, we can get all the way to pOH by first converting to pH, and then from pH converting to pOH. So this is just like another similar thing to stoichiometry, where we just convert from one thing to the other to get where we need to be. And finally, we can go from pH to pOH by doing 10 to the negative pOH, or we can go this direction by going negative log of the concentration of OH-. So there you go. This little diagram kind of lays it all down for you. If we have the H+ concentration and wanted to find the OH- concentration, we would convert to pH, and then from pH to pOH, and then from pOH to OH-. If we have the pH, we can find the H+ concentration, we can find the pOH, and we can find the OH- concentration. So any of these 4 pieces of information can be converted to any of the other ones using these calculations. So here's an example. Let's say we have a solution and we know that its pH is 4.7. Now we want to find these other 3 pieces of information, and we can use this little table right up here to do it. So we're starting off with pH. We've got that right there. Let's first go ahead and get the pOH. Okay, so we're going to fill in this little box by going from pH to pOH, which means we're going to follow this little path right there. So 14 minus the pH will give us our pOH. And if we subtract 14 from the pH, that gives us a pOH of 9.3. Alright, next let's go ahead and find the H+ concentration. So we have the pH, we know that the pH is 4.7, and so to get the H+ concentration, we're going to follow that little path right there, which is 10 to the negative pH. So if we do 10 to the negative of 4.7, we find out that the H+ concentration is 1.995, so let's call that 2.0 times 10 to the negative 5th. And the units of that would be molarity. The last piece of information is the OH- concentration. So to get to OH- concentration, we're going to take this little path right here from the pOH. So the pOH is 9.3. 10 to the negative 9.3 will give us the OH- concentration, and that winds up to be roughly 5.0 times 10 to the negative 10th, and the units of that would be molarity as well. So hey, this is pretty cool. With one piece of information, we started with just the 4.7 for the pH. We were able to calculate these other 3 pieces by using this little table right here. Got plenty of practice with this. There's a couple practice problems on the website, and there's a quiz as well. Good luck. I'll see you later.